Okay, so we're going to look a little bit about antenna patterns. And a little bit about antenna modeling. So we said directional antennas are said to have gain in a specific direction. There's actually no power gain. And since it's passive, there's, power out is equal to or less than the power in. So the total power emitted by the antenna, regardless of what type it is going to be the same, whether it's an isotropic or a Yagi or whatever. So what is the difference in radiated power between a lossless antenna with gain and an isotropic radiator driven by the same power? It's just to see if you were paying attention. You always have to wonder about those ones where I have the really long answers. Okay. One of the ways that they show the performance of an antenna is with a field strength plot. And there's really two kinds. There's azimuth and elevation. We're showing an azimuth plot, okay, which is basically looking down onto the antenna and the pattern that it has. So this is some form of beam antenna. You can see all the power is in this one lobe in that direction. Typically, that would be what you see with a Yagi or like a quad loop, something like that. And you can do this by hand, by going around doing the measurements, or you can do it from a modeling program like EasyNet, probably the one most people use. And there's different variations for user interfaces for it. But this is a fairly typical azimuth pattern for a beam antenna. And you'll see what we call the front to back, okay, is where the front is referenced to 0. And the back is crossing kind of halfway between -12 and -24. So we'd say that was -18 dB down. So that'd be the front to back ratio, 18 dB. If we did a front to side, then you try to figure out where this one was. And because I know the answer, it's 14. It's kind of hard to tell on these charts, but this is what you get on the test.
So you're saying that there's a measurement front to back, but you can also have a measurement front to side.
Right.
Okay, and that, okay.
Because one of the side effects of maximizing gain is you get more side lobes and maybe a larger rear lobe. So one of the things they play with is the spacing of the elements on the Yagi and the length of them, which you can affect all these kind of things and get different patterns. Sometimes you don't want maximum gain. You may want to have the best front to back ratio. So you have a null, almost a null on the rear. So you can tell whether or not you're getting a signal from this direction or that direction. That's the problem with a dipole. It's directional, but in two directions. So you don't know if it's coming from here or it's coming from there.
Will it always be plotted where the front lobe is at that outer edge?
Typically.
So,
and that will usually be at 0. Because that's where they're measuring it from. And these really only show what's called the far field pattern. When you get into what's called near field it's just a jumbled mess because there's all sorts of things that interact. So you have to be far enough away from the antenna where you have a stable radiation pattern. And they call that far field. Exactly that, how far that is, I'm not sure, but it will have to do with the wavelength that you're operating at. So once you get to what's called far field, the distance no longer has any effect on the pattern. The pattern will be the same, just bigger. So what is the far field of an antenna? Delta. Radiation pattern stays the same. Okay. We can measure the width of the main lobe, and we call that the beam width if it's a beam type antenna where you have a lobe in one direction. And we normally measure that at the 3 dB points. So you can see on this chart, there's a minus 3 dB line. So where that pattern crosses it on both sides will determine the angle, which they call the beam width. So I would guess this being, I don't know, that's 15, 30, 25 maybe, 24 times 2. So it's double that. So, well, yeah, I didn't read it. I was saying it's 25, but it's kind of a guesstimate. So that would be a 50-degree beam width. So what is the 3 dB beam width of an antenna radiation pattern shown in figure 9.1?
Wow.
I bet it's the same.
I don't quite understand because that's not actually the widest point.
No, it's where it crosses the 3D point. The 3 dB down to half power.
So
It's the half power points, just like you do for a bandpass filter.
okay.
And it goes, you measure it from the lower and upper 3 dB half power points. They call them cutoffs.
Okay.
Same thing for this. That's, once you get at an angle beyond that, you're less than half power. And that's just a standard for measuring a lot of things, the half power points. Front to back ratio is to measure how directional the antenna actually is. So the higher the ratio, the more directional, not necessarily the highest gain. And like in this chart, they're showing, that rear lobe is around halfway. You could argue it's 17, 19, whatever, but around 18 dB. So would be the front to back ratio. So what is the front to back ratio of this pattern?
It's really hard.
Well, they could put a different one in. I could have given you different numbers.
I know. But you didn't.
Front to side ratio. So in this one, what's our front to side ratio?
Kind of close to 12,
Mm-hmm. So 14.
not 12, not 18.
That would not come short.
Yeah, it's best guess. So what do you think it is?
Delta.
Delta? Delta. Okay, we also have elevation. Where you slice it vertically. And see what the pattern is. And you can see that in this case, it's probably high enough, probably more than a half a wavelength high, so you're getting these extra lobes. So even though the largest lobe is down here, and if we take where this peak is, say, what, 7.5 degrees, that would be what's called the takeoff angle. You do that, you measure that from the largest or most powerful lobe. But because you got these other lobes, you also got power going out in these directions. So even though this one is the best takeoff angle, which means you're going to, when we talk about maybe next week, propagation, refractions, you're going to get the longest refraction from the lowest takeoff angle. But you don't have as much power in it. That's why usually half a wavelength gives you a pattern where you basically have a single lobe, but your takeoff angle won't be quite as low. So it's one of those trade-offs. You get more power out, but at a higher angle. And like I said, we'd say this was a 7.5 degree elevation or takeoff angle. So what type of antenna pattern is shown in 9.2?
Alpha.
Alpha.
Now, what we're talking about before, we were talking about the width of the signal, right? And now we're
The
talking.
horizontal width.
Yeah.
Now we're talking about the elevation.
Okay. So, is that,
So top down and side on.
okay.
It's like taking a slice of it like horizontally versus vertically for the surface chart.
Okay.
Now, they don't do it in some of the, like EasyNet. You can do those plots. You can also do a 3D one, which will give you a 3D kind of a wireframe picture of the pattern that you can rotate around and see it better. But this is the way they do the typical measurements to compare antennas. So you may see one listed and they'll tell you what the takeoff angle is, tell you what the beam width is, tell you what the front to back gain, all those things. So what's the elevation angle of peak response in the pattern shown? If you paid attention, you know the answer.
That's the problem. I never pay attention.
Let's go with 7.5. What is the front to back ratio of the radiation pattern? So we're going to do front to back vertically.
Okay.
You do it the same way.
Okay.
It's like slightly beyond 30, but not by much.
So
It's actually
30.
wrong.
Yeah, I'd say it's not quite 30.
Could you go back to the last one, please? What?
There's something in this room that affects my mouse.
I'm sorry, maybe we should do this later. Okay, where did that come from? Where did that number come from?
Where this peak is on the lobe. See, it's 0 to 30. So this line would be 15.
Gotcha, okay,
So it's about halfway. So it's around 7.5.
thank you.
and we did that one, okay. Okay, so I mentioned EasyNet, which is one of the modeling programs. It's actually based on NEC, which is the numerical electromagnetic calculator that was developed as a Fortran program by Lawrence Livermore Labs. It's a fairly old program. EasyNet uses that calculating engine with a different front end on it, where you can input parameters in like a spreadsheet kind of form or tables and model antennas with it. So it's a little easier to use than having to run a Fortran program. One of the things it'll do is give you an SWR plot. So it'll show SWR versus a frequency span, however much you want. You can do the polar plots for the far field of elevation and azimuth. Like I said, you can get a 3D plot of that. Show you what the antenna gain is. It'll tell you what at different points, what the impedance is in R plus JX form. So it'll tell you how much inductance or capacitance you're seeing with it. So there's a lot of information you can get. Shows you currents on the elements, what the current waveform looks like, where the high current and low current is. It uses what's called method of moments. What you do is you divide the antenna elements up into small increments, and it calculates for that little increment what the current is at that particular frequency, and that's how it plots it. You can have as many segments as you want. In other words, you can divide the wire or the elements up into thousands of segments if you like, but because it has to process each one, it's going to take, well, infinitely long if you had an infinite number of segments to calculate. But you have to have a minimum of 10 segments per wavelength. Otherwise, you don't get very good results. But it's kind of like, we mentioned the Nyquist sampling where you got to do it twice for the frequency. Well, same kind of effect here. You've got to have at least 10 samples per wavelength distance. What type of analysis is commonly used for modeling antennas? Bravo. It actually came from civil engineering, the way they calculate certain things. What's the principle of a method of moments analysis? Any more alphas?
Oh, I'll say alpha.
You just follow Amy.
Must be right. See, I follow the principle of it's better to be thought a fool than to open your mouth and remove all doubt.
That's true. Right. Yeah.
I am who I am.
It assumes a uniform current for each segment. So that's how it's doing the calculation based on what the average current would be for that little segment. And I mentioned this, the more segments, the more accurate it is. Too many segments, it takes too long. You sit there for hours. Depending on your computer, on a laptop, you got a few hundred segments, it'll do it pretty quick. Depends on the frequency spectrum. I mean, the wider frequency band you want to look at, obviously, the more calculations it's got to do. And if you don't have enough, it'll usually warn you. You come up with some error things and it'll give you a thing to check and fix it with what it thinks is at least the minimum you need. But the key is at least 10 per, oh, they say half wavelength. Okay. I thought it was a wavelength.
So that conference sounds, very interesting actually, but, you know, I'd like to see it in action. I mean, talking about classes, I mean, that would be, because how do you get all that information? I know that we don't need to do that here, but I'm just saying that
Which information?
the program, where do you get your information?
Oh, you can download it. It's free.
You download the program,
Uh-huh.
but then how do you know what you're taking from your antenna and putting in there?
Well, that's the tricky part.
Aha,
You have to put the data in. Or, I mean, you can create your own antenna. And that's kind of what it's used for, to model different antennas, not necessarily a real one. And they'll have a bunch of samples that you can call up, that you can modify. You can just do it from scratch.
I see.
And you define it like, you'll say, like say you want to do a dipole. You would define element 1 or wire 1, excuse me. And you give it an XYZ starting point and an XYZ ending point. So ideally, you kind of want to make Z the same on both ends, and maybe say X is the same, and then do it over Y. And do wire 2 separated a little bit, the same kind of thing. And then connect it with a balun or transmission line and feed it from, select a source to feed it with. And then you could actually do a plot of it. And one of the things, when you define the wires, you have to tell it how many segments you want for that wire. So that's where you get into you got to have the minimum. And then you just can run the different models. It will show you kind of what the antenna looks like in a straw man sort of thing. And you can do the plots and SWR and all that.
What's the name of that?
Easy Neck, Easy NEC. I think it's 7 now. The guy that did it retired and put it on. They used to sell it. Now it's free, but they're not doing any updates to it. Okay, so what's the disadvantage of decreasing the number of wire segments below the 10 segments per half wavelength?
Sure.
Okay. All right. Actually, and the free one, based on the NEC2 engine, doesn't do ground very well. If you want to really get into it and do good modeling over ground, different types of ground, then you have to pay $100 for the NEC5 engine, which will work with it. But unless you're serious about playing with models, I don't think you want to spend $100. Well, that was an easy one.